Good morning, Dr. Carney. To start off, I did my name reaction video project on the pain rearrangement. And to get right into it here, kind of just talking about the mechanism and what this actually is. The reason it's called the pain rearrangement is because it first starts with the rearrangement and the mitigation of an epoxide. And this particularly occurs in 2,3 epoxy alcohols. So if you see here, you're starting here, and you have your 2,3 epoxy alcohol, and you have an OH group here at the end, which then is deprotonated by a water molecule in the presence of a strong base. The presence of a strong base here takes us to our next product, and we have this negative charge on the oxygen here at the end. So what ends up happening here is that you have this bonds to that number 3 carbon through the mitigation, and then you're going to have the negative charge shifted to this oxygen here. So you're left with this, which is the epoxide's now moved off the number 3 carbon, and then you have your negative charge on your oxygen on the number 2 carbon, which is then protonated by a water molecule. And then that takes us into the SN2 mechanism. So the reason this is SN2 rather than E2 is because it's typically used in the presence of bulky base, such as the sulfur tert butyl group used here. And so you have that sulfur tert butyl attacked to this number 3 carbon, or excuse me, the number 4 carbon, to open that ring. And so when it opens the ring, you're left with your hydroxide group from the rearrangement, and then your oxygen with the negative charge here, which is then reprotonated again by a water molecule, and you have your sulfur tert butyl group here. And so that ends up leaving you with this alcohol here. But really, in order for this reaction to occur, you have to have that epoxide mitigation through the rearrangement, which is why it's called the pain rearrangement. And it allows you to bond bulkier bases to these alcohols. And touching on the reaction diagram here, so as you can see, this goes through 3 transition states, here, here, and here, with 2 intermediate phases. And kind of what you're seeing here is multiple, intermediates here and here, but it's really difficult to tell whether it's an exothermic or endothermic reaction, due to the fairly even level of both the energy of the reactants and the products. So that kind of left me guessing for my calculation section, which I'll touch on later. Before we get into that, I want to get into a literature piece I found. And what that talked about is, let me pull up the title here. It's exploration of epoxidation ring opening strategy for the synthesis of lyconidan A and the discovery of an unexpected pain rearrangement. And so I'll send the link in the Dropbox to the citation of the reaction. But what it gets into is certain Lewis acids can actually lead to an unexpected pain rearrangement. And they found this interesting in the study, and it didn't really go into depth into so much as why that occurs, but rather how further research should be conducted in order to see how this may be able to benefit chemists in the future with organic synthesis. And so they couldn't quite figure out why, but the point is that the presence of a certain Lewis acid can actually cause this 2,3 epoxide mitigation. And I found that pretty interesting as in how we can conduct further research to better our understanding of this whole process. And so, like I said earlier, getting into my calculation section, I ended up finding out that the reaction is exothermic to the change in enthalpy here, and as you can see, the change was a negative 370 kilojoules per mole, which is when, let's see, can you see it like that? No, that way works better. See the best way to do this here. So basically, when I plug that in, the change in enthalpy into our Gibbs free energy equation, I used 298 Kelvin as the temperature because that's standard temperature, room temperature. And entropy in a substitution reaction is kind of it's kind of negligent because it's so small. And so what I found is that delta G was less than 0, meaning that it's a spontaneous reaction occurring in the forward direction. And when delta G is greater than 0, that means that K is greater than 1. And when K is greater than 1, let's see, you can read it like this. No, you can't. So basically, when K is greater than 1, that means that the reaction favors the products and that it does occur in the forward direction. So I did find some pretty interesting things about this reaction, and I just hope that you like this kind of short bit of information that I had to give on it. And I thank you for a great semester, and I hope you enjoy your break. Thank you.